Hello everyone. Now I hope you are good at your home. So let's start our next topic, that is work done. Work done in rotating a dipole in uniform electric field. So in previous topic we have studied that when electric dipole is placed in uniform electric field, it will experience a torque. So this is a dipole that is placed in uniform electric field and making angle theta. It will experience the torque. And this electric dipole tend to align in the direction of electric field. In this way it will get aligned because these charges will experience the force. These charges will experience the force. Due to this equal and opposite forces they will experience, and they will try to align in the direction of the electric field. So now we have to find out the work done now. You know that this dipole will execute only rotational motion, no translatory motion. It will not execute translatory motion, but it will rotate in this uniform electric field. So generally you see, after rotation it will align in the direction of the uniform electric field. In this way it will get aligned. In this way it will get aligned. So if we want to rotate it against the electric field, or we can say that against the direction of the torque, that we can say that anti-clockwise, in this way, anti-clockwise you say. In this way we want to rotate it. For that we have to do the work against the electric field or against the direction of the torque. So let us suppose initially it is aligned, this dipole be aligned and make angle theta 1 with the direction of the electric field, and we want to rotate it anti-clockwise so that it will come in this direction. It will come in this position and make angle theta 2 with the direction of this electric field. So for that we have to do the work done. So let's start the derivation first. We know that when electric dipole is placed in uniform electric field, it will experience a torque, that is tau is equal to Pe sin theta. This is the torque. Due to this torque it will rotate, but we want to rotate it in opposite direction, that is anti-clockwise. This torque will bring it in clockwise direction, but we will do the work against this torque. So for that we will do the work. Okay, I think this is clear. So you know that we know work is equal to force into displacement. This is the work done, this is linear force, this is linear displacement. But here we are dealing with the rotational motion. So we will do the work W, torque, and here we have, in place of linear displacement, we will do here angular displacement. But during rotation we know that the angle, this angular displacement will change. We can say that this angle is going to be changed. So torque, this angular displacement is going to be changed. Due to change in this angle, this value get changed. So torque also get changed. So we can say that during the rotation the torque is not uniform, but it is variable. So we know that when we have a variable displacement, or we can say that variable torque, not displacement, variable torque, then work done will calculate in this way, dW and d theta. I think it's clear. So we will rotate this electric dipole by undergoing small angular displacements, small angular displacement, and during those small angular displacement there is small work done. It's clear? So let electric dipole be displaced through small angle or angular displacement. We can say that angular displacement d theta. Then small work done is dw. Torque, that is turning effect. Due to this turning effect, this dipole will rotate, and angular displacement d theta. And this torque we have written in this equation number 1, Pe sin theta d theta. So in order to have total work done, we will integrate equation number 2. So then we'll get total work done, that is equal to dw, and work done will do from 0 to w. Earlier this is the initial position, of the dipole, this is the initial position of the electric dipole and making angle theta 1 with the direction of the electric field. So here work done is equal to 0 because we are displacing it, we are doing the angular displacement from this initial position. So here work done is 0, this is the final position, so here work done, that is equal to w. I hope you understand this. So next, Pe sin theta d theta. Now this theta, that will change from initial position theta 1 to theta 2. Clear this is? Now we will get W is equal to electric dipole moment P, that is constant, E uniform electric field, that is also constant, and we will integrate sin theta d theta, theta 1 to theta 2. So we know that the integration of this sin theta, that is equal to minus cos theta, and range is theta 1 to theta 2. We can write minus Pe cos theta 2 minus cos theta 1. This is the range, final minus initial. Now this work done will store in the form of potential energy. So we can replace W with U, that is equal to minus Pe cos theta 2 minus cos theta 1. So this is the work done, and this work done will store in the form of a potential energy of the electric dipole in the uniform electric field. So we will replace it with the U. So this is the final expression of the electric potential energy. Equation number, we can write this equation number 3, this equation number 4. Now we will discuss some special cases. First one is, if dipole is rotated from stable equilibrium position to unstable. You know that for stable position theta 1 is the initial position. This is the initial position and this is unstable equilibrium position. That is equal to theta is equal to 0 degree. We know that for the stable equilibrium position, the angle theta that is equal to 0 degree. The theta is the angle between electric dipole moment P and E, and theta 2 is the final position, that is unstable equilibrium position. So for this, angle is equal to 180 degree. So when we will use these two values of the angle, we will get minus PE cos 180 degree minus cos 0 degree, will get minus PE minus 1, that is equal to plus 2 PE. This is the electric potential energy of the electric dipole moment when it is rotated from stable equilibrium position to unstable equilibrium position. Second one is, now see, let us suppose we have placed this electric dipole perpendicular to the direction of this electric field, that is theta 1 is equal to 90 degree. Theta 1 is equal to 90 degree, and we want to see that this dipole will rotate anti-clockwise or clockwise. Suppose we are placing the electric dipole perpendicular to the direction of electric field, and we want to see whether this dipole will rotate clockwise or anti-clockwise. So for this, if dipole is placed perpendicular to the electric field, and rotated to any other position, that is theta 2 is equal to theta, and for perpendicular we know that theta 1 is equal to 90 degree. This is the initial position, this is a final position. Then energy is minus PE cos theta and minus cos 90 degree. So then we have minus PE cos theta u, and from this equation we know that P is vector quantity, E is vector quantity, and this is cosine of angle theta. So we can write u is equal to P dot E, dot product of electric dipole moment and electric field. So dot product of two vector quantity is a scalar quantity, and this negative sign indicates that electric potential energy is minimum. So when we will discuss the sub cases of this second case, first one, if electric dipole moment and electric field are parallel to each other, then u is equal to parallel to each other, then theta is equal to 0 degree. So that is PE cos 0 degree, that is equal to minus PE, that is equal to minimum potential energy. Clear this is? And second sub case is if P and E are anti-parallel, then theta is equal to 180 degree. So we can write U is equal to minus PE cos 180 degree, that is equal to PE, that is equal to maximum potential energy. So here from this we come to know that when the electric dipole moment is rotated anti-parallel to the electric field, then we have to do the maximum work, maximum potential energy, because we are doing the work against the torque here. It's clear? So this is all about the work done in rotating the dipole in the uniform electric field. So this topic you have to follow, you have to go thoroughly for this topic. Thank you.